All right, let's get this show on the road. Make sure things are plunking along. Hope you're doing well today. This is Jared with another Zephyr 101, and today we're going to be talking about asynchronous UART. And this came in from a request in my forum. Originally, I thought I could help them kind of directly there, but then I realized a lot of other people probably had the same problem that I did when I started playing around with Async UART. So let's jump in. If you haven't already subscribed, hit that subscribe button, hit the like button, and all the good stuff. I really appreciate you guys being here and doing all those things, because that's what kind of brings the word out, shares the goodness, you know, however I can say. We got a spooky spell going on CircuitDojo.com for over the weekend. So if you want to get some Circuit Dojo related items, including accessories, head on over there. You can use the code SPOOKY for 15% off. Yeah, that's one thing you can do to help support me here in the show. I don't really make a lot of money off the off YouTube, but anything helps. So I really appreciate it. So here's what's going on today. This came from Krupis. I'm having a lot of trouble understanding how to use Async UART. So let's dive in a little bit here. The Async UART implementation is probably the most complicated and frustrating things I've run into in a while, coming from maybe other implementations which kind of abstract all that information, all that kind of complexity away. So there's a lot of things that might be new to you if you are setting this up for the first time, and it's a little finicky, and without understanding exactly how everything works, you'll be spending some time getting to know all the intricacies, because it will drive you crazy. So we will go through all the steps as much as possible. I have a driver example that I'll be going over, and also one that's also included in NCS in terms of one of their samples is using the Async UART API as well. So at the bare minimum, we got to make sure that serial and the UART Async API is turned on. One thing that you might notice is there are other APIs, like the polling API and the other one, the interrupt API. I forgot what exactly the name of it was. But you can turn all these things on at the same time if you want, but they can't be used at the same time. So you kind of have to choose at the beginning which one you actually want to use. So keep it simple here, just making sure those two things are on. Depending on your overlay, your DTS, you might have to make some configuration changes, do that as needed. There's nothing really in the overlay that I would say needs to be turned on or set correctly for this to be working. I think the only big thing here is the biggest caveat in Zephyr is making sure that you actually have support for those APIs on the device that you're using. So for instance, Nordic has implemented the Async API for their chips, but your mileage may vary depending if you're not using Nordic, but it's all about the same idea here. It's using the same API. So for instance, I'm changing the speed. So I'm using an HPMA 115S0, which is a PM2.5 sensor air quality. So that guy actually uses 9600 baud, and I'm also just setting the driver information, so on and so forth. So yours might be different. You actually might be using the interface directly, or you might be creating your own driver. So again, your particular situation may dictate differences here. Jumping into the code a little bit more. So there's this RX timeout, and I'll touch on it a little bit more, but it's somewhat important for the Async API UART implementation. And for this, I'm using a driver. So one thing that I try to stray away from is using any dynamic memory allocation if I can. So for the design purposes of this is I wanted to create a buffer with the size two times the size of a frame from this device. So the frame of the HPMA 115S0 is 30 something bytes or somewhere in there. So it is just giving me enough buffer space to capture maybe two of those frames if they happen at the same time. In this case, this device sends a frame every 1 second. So if I just want to pull and just listen for one, then I can just listen for one and I can turn off the results and move on. But the args timeout, I believe, is in milliseconds, I think. So that's just something to keep in mind. I'm setting it up in the init function, but this could be in your main as well. The first two structs are kind of confusing, but it's basically just getting some pointers for some data that is getting shared, especially the device. So in the config, that bus has been set elsewhere, but that is the pointer to your device. So device DT get is pointing to that config bus. So we're just making sure that it's ready. I think that should be done anywhere in your code, especially if you're accessing a device, just to make sure it is ready. If there's make sure there's no errors. The next, probably the most important thing here is making sure that you set your UART callback. This is particularly important for the, this is particularly important for the async implementations, because this callback is going to be used to let you know if there's data, if there's an event that happened on the bus, if there's errors, if it's been stopped, so on and so forth. So this is the kind of the crux of everything, is making sure that you've set it correctly. The first argument there is the pointer to the bus, to the device, and the second is the callback, and then basically the last parameter is just like a void pointer, so you can provide any context data, whatever you want, into it. So when that callback is called, that pointer is actually given to you as an option, and you can use it for whatever you want to do. Now, we've set everything up to the point where we're kind of ready to receive data. It's pretty simple, straightforward. I will show you the implementation, or at least partially, of the callback. But really, the only thing we got to get going is enabling the receiver. So in this particular driver, I've included a link to it in the description below. But what I've done here is I'm using this RX buffer, and it's just a statically allocated buffer. So every time I go to receive a frame from the sensor, I'm just making sure that it's empty and set to 0 to make sure there's no funky data in there. One thing I like doing for just making sure that everything is turned off, you could have a situation where it's still turned on for some reason, but it's good to do that for these kind of situations where you're turning on and off the receiver. This is so my caveat here, you're probably like, Jared, why are you turning off the receiver again? Well, the biggest reason is that the receiver for the UART uses a crap ton of power from a low power standpoint. So it uses like a milliamp or 500 microamps, something like that. So for battery constrained applications where things are tight, you do definitely want to disable things or use the LP UART implementation. I kind of talked about that in my last video on using Bluetooth, connecting Bluetooth to the NRF9160. That is the same interface, the same driver, I guess you could say, that you can use to kind of save a lot of power. So this just something to keep in mind. It's all really dependent on your application. So for me, I'm using a straight up UART. I'm only listening for a frame when I need it, and then I'm turning everything off, but you got to kick it off somehow. So to kick it off, we're using this UART RX enable, and you can see I'm providing the bus. I'm providing a pointer to the buffer. So this is the buffer that's going to be filled up when you receive data. And I'm just saying, hey, I want to receive a frame size +1. So it's like frame size and maybe a null character or a new line or whatever. I forget exactly what it was, and then also we're setting the RX timeout. So this is the important bit. So you can either say, hey, I want to receive a certain amount of bytes, or you can say, hey, I want to receive the size of the buffer, but set a timeout. And what will happen is, say you receive like 3 bytes, and nothing happens for that 10 seconds or 10 seconds. It will actually generate an event and say, hey, there's some data ready if you want it. And then what will happen is you'll get the size of the number of bytes that are being provided and things like that. But we'll dive into that in the callback. So the callback structure, that first argument is provided the device. You got the event in the middle there, and that context, that data, that void pointer that you can use for basically anything. And here are just a list of all. If you look towards the bottom here in that switch statement, this is kind of a bunch of events that can be generated by this callback. The most important one being RX ready. And this is where you're going to be able to get the data from the UART interface, whether you've received the amount of bytes that you requested, or that there was a timeout. You received some bytes, but then there was a timeout. You didn't fully fill up the buffer, or so on and so forth. So, or if you filled up the buffer completely. So those are kind of like the three situations where you'll have data to take care of. Excuse me. You can see that you got that event. It's with a pointer to the data. Provides the length, so you have an idea of how many bytes that are provided, because it could be 1, it could be 2, it could be however many that you indicated, or even more. So it really depends on your situation. And then you got a pointer to that same buffer. So why not just use the statically allocated buffer pointer? Well, it depends on your application. If you want to use a dynamic memory allocation, then that pointer is essentially the only pointer to the memory that you allocated in memory somewhere on the heap. So that's an important thing to have, because that's the only way you're going to be able to get your data and also free that memory when it's not being used. So keep that in mind. But in this case, I'm just doing everything statically for this driver. So that ready event indicates you have data. You can get it as you need to and use it. I highly recommend that you actually copy it or use it elsewhere. You don't really want to do a lot of processing in this callback, only because it's going to prevent any other UART events or anything else from happening. So it's a quick, hey, I got data. I'm going to copy it to a message queue or a FIFO or whatever. Just get it out of the way, because you want to make sure that this callback can handle more requests as they come. You saw there was other one called RX buff request, and this is for situations where you want to know for memory allocation purposes that, hey, it needs another buffer so it can continue receiving data. So it receive the number of bytes, or it's full, so you gotta handle that. And this is particularly important for the dynamic memory allocation situation. So you'll receive that request. It'll happen probably just before you get the RX ready event that's happening, and then you can actually see that in the other sample that I put in the description. That's the one from Nordic. They actually have a couple of samples where they're using it, including the UART RX buff response. So it's basically, hey, this is the response. This is the new pointer to the new buffer I want to use, and go ahead and use that. You can also use that function to point to a statically allocated buffer if you want as well. Maybe you have two buffers and you just flip-flop between the two. That is also something that you can do without having to dynamically allocate or use malloc. But like I said, they can be allocated. I'm gonna beat this to death, but you can allocate dynamically or statically. Dynamically is more complicated. It'll probably drive you crazy. So if you can avoid it and just use the static, then by all means do it that way. So that NCS sample that I just referred to earlier, it uses a kernel macro. It's called a memory slabs, and essentially just give you a block of allocated memory for that particular use. And then you can allocate free memory in that particular location. So you're actually kind of using a predetermined piece of memory, kind of like your own very sub heap kind of thing. So this is actually the function. So I just borrowed it from the sample that I just referred to, the Nordic one. They just created this RX buff alloc, and it's just creating or allocating some memory out of that slab that you just create. So, but you can see there's some atomics here, or there's a reference counter. There's some things going on. So It gets a little bit more hairy when you start doing more dynamic memory allocation. So I try to avoid it when I can. But this is an example. This is at the top of that file, the usage. You're creating this UART RX lab. There's a block size. There's a block count. There's alignment. You're creating this block of memory that you can use for the receiving of UART events. So, and when you run out, you run out. So the idea is, if you can process everything as fast as possible to make sure that you're not going to overuse or run out of memory. So you got some other events here that are also useful just for your kind of like for your context or just knowing what's going on. So for instance, if you're doing any dynamic memory allocation for the transmit side, so when you're transmitting, you can provide a buffer to the function for pushing data out, and maybe you want to know when it's done, so then you can free that buffer, so that event is perfectly great for that. If there's errors that happen during the usage, you might get a TX aborted or an RX stopped event. The RX stopped event will actually provide you a little more context as to why it was stopped. Usually it'll provide like an error. It's all part of that data struct, so you can actually click into error and see what's going on, and maybe do different things as necessary. The more complicated implementations, the async UART ones, or the dynamic ones where you're allocating memory, these particular events are important because essentially you've allocated memory that's going to be used to receive data or publish data, and if an error occurs, you have to handle that somehow. Otherwise, that memory is allocated and accounted for, but then it's not used anymore. So that's not good, because if you don't free it or handle it, you're gonna have problems, and you're gonna get an overflow or something like that. So I'll harp back on just making sure that servicing any events that happen in this UART callback is really important, and making sure that keeping it at a tight, I guess you could say, a tight loop, just making sure that it's very tight and there's not a lot of extra processing or things happening there. Tweak the RX timeout as you need to. So for me, it didn't really matter, because I was expecting just a certain amount of bytes, and then choosing whether or not you're going to do dynamic or static. Dynamic, much more complicated. Static is really for applications where you know the size, it's not crazy, you're not streaming a lot of data. But dynamic is great if you are doing a lot of streaming or handling data that is not known in size. So again, this is all application dependent, so I hope that helps. It is the most complex, but it's kind of like the most robust. So when I was using some of the other options, the interrupt driven and the polling version, I was having a lot of trouble just getting the correct amount of bytes that I wanted for different things. So when I was first started playing with this, like 2 or 3 years ago. So it is, especially because underneath this UART implementation uses some of the like DMA functionality of the NRF52 or NRF91, all of the same peripheral. So it takes advantage of those things. So it just makes it a lot easier, and you don't lose as much data because it's kind of handling those things, as long as you're providing the buffers and you're kind of servicing that callback as needed. So biggest thing, the biggest gotcha is understanding the data, the buffers, how to provide them if you need to, and then kind of choosing whether or not you want to do dynamic or static. I'd recommend static, but you can also check out that sample in the description box, and you can see how Nordic did it with dynamic allocation. And then you have a whole slew of events that are provided by the callback. You can use those as necessary to handle that dynamic allocation, or it's like, hey, okay, I'm done transmitting, I can turn off the receiver or something like that. So depends on your application again, so you can really you can customize and really tweak it to get the way you want it to go. So again, everything's down in the description box below, and just if you'd like to see more, this is it, I think. If you'd like to see more, or if you want me to dive in a little bit more, maybe provide some more examples, leave a comment in the box below, and I'd love to hear from you. let me see if we got comments. We got a comment from Scott. Aloha, very interested in this topic. Yeah, well, Scott, I'm glad you're here. It's complicated, so I wish it wasn't so much. People coming from Arduino, even from like the Nordic bare metal SDK, it was a little bit easier to just kind of get things working. So because Zephyr has to fit inside this, has to be generic enough where it will work across different platforms and different systems. This is kind of what they came on in terms of the different UART APIs. So your guy is asking, is the Async UART async hardware or software? It's, how do I say this? It is software that is designed to take advantage of the hardware inside your chip. So the async, any type of async implementation is usually directed towards a hardware implementation of like a DMA interface. So you're providing what happens with DMA is you set up some registers, you say, hey, I want to receive some bytes, and I want this peripheral to send bytes to a particular memory location without the need of any CPU. So it's actually a hardware process that's happening on the back end. It's actually just a piece of hardware that's on the side of the CPU. That way the CPU can kind of go off and do things while it's receiving information from the UART peripheral. Now, back to the software level, that the Async API is actually taking advantage of that and using that functionality down below, but it depends on how it's implemented by the vendor or by the community for a particular chip. I'm pretty sure for Nordic, it's using the DMA functionality. It's called EasyDMA. But that's the idea. It's kind of a both, and it's like kind of both asterisks. It depends. I feel like I say that a lot, but it really does. But for you got another question. Is it limited to MCU capability? It might be. You have to check and see if it's implemented. If you turn it on and you try to, it'll actually. So I actually used it on a chip once where it wasn't implemented. It was like an STM32 with LoRa built in, something like that, and I couldn't get the Async UART. It would just say when I went to compile it, it basically barfed at me and said, "Hey, the Async API is not defined." They just put it in like an error in the code somewhere, and it just said, "Hey, it's not defined. You can't use it." So again, depends on your chip, depends on your particular instance. So, and then Costas, yes, Async use DMA. Christopher, thanks, really helpful. You're very welcome. Glad to see you here, Christopher. Cool. And yeah, very interesting. Thanks for that. So no problem. I'm glad you guys are here today because this is one of the stickier points, more advanced points in Zephyr, just getting UART working, which is funny. It's like, it's UART. It should be simple, right? No. Ugh. But I think that's it for today. If you'd like to jump over to jaredwolf.com and subscribe, I always send out little emails and messages beforehand. There's also a deal going on, like I mentioned before, on circuitdojo.com. If you just use the code SPOOKY, 15% off. So you're very welcome, Costas. But I'm really glad for everybody being here. Thanks for being here, and I'll see you on the next rendition of Zephyr 101.